now conclude the lecture on elastic wave propagation by describing equations of travel time arrivals of waves at given sensor locations. Note that these travel time equations are presented here because they provide an insight into the relationship between recorded data and the locations in the subsurface, which cause reflections, refractions, and diffractions. Be prepared to see more mathematics in this lecture than in the previous ones. However, these are basic mathematics and are well illustrated. As we discussed in one of the introductory lectures, the information contained in seismic data consists of arrival times and amplitude of reflected waves. Our focus in this lecture is on travel times of reflected waves. These travel times tell us the speed at which the waves travel through the rock formation. They also allow us to locate reflectors, which produce the reflected seismic data. Some of the key outcomes are to familiarize yourself with the notions of normal moveout, or NMO, RMS, or root mean square velocity, updip and downdip shooting, and Dick's formula. Understanding the difference between hyperbolic moveout and non-hyperbolic moveout. Understanding the difference between refracted and reflected seismic surveys. Here are the components of travel time equations we are going to discuss. We will start with the travel time of reflected waves at the horizontal interface. Here is the configuration under consideration in this lecture. The source and receiver distances, that are offsets, are denoted by x, and depth from the source to reflector is denoted by h. We assume that we have only one shot point, but multiple receivers. So x is a variable, while h is fixed. Our objective is to derive the travel times of reflected and refracted waves as a function of the receiver positions. Before beginning these derivations, let's once again examine waves spreading throughout a homogeneous medium, where they propagate from the source position to the receiver positions without encountering any obstructions. Such events in seismic data are called direct arrivals. The travel times between the source and receiver are straight lines. Time equals offset over p wave velocity for p waves. Time equals offset over s wave velocity for s waves. Again, here, x indicates the distance between source and receiver. That is offset. The travel time derivation for a wave reflected from a single horizontal interface is straightforward. In this figure, we see that travel time from source to receiver is AB, source to reflector, plus BC, reflector to receiver, over velocity. The travel time equation in this case is not a straight line, but rather a hyperbola, as we can see here below the figure. This is our first important result in this lecture. In other words, travel time equation for a horizontal interface problem can be arranged in the same form as the equation of hyperbola. Y is t, A equals 2h, B equals 2h over velocity, and x is unchanged. An important aspect of this travel time equation, which is used extensively in seismic exploration for velocity estimation and imaging, is normal moveout, or NMO. NMO is defined as the difference in reflection travel time from a horizontal reflecting surface due to variations in the source-receiver positions. Here is an illustration of travel time equation for reflected waves. Notice that we can describe the travel time equation by using the travel time at normal incidence T0, and the curvature is described by T_NMO. T0 equals 2h over velocity. Above the reflector is the two-way travel time at the source, that is, at x equals 0. Thus, NMO travel time is equal to the actual travel time minus T0. Thus, NMO is equal to travel time at offset x minus the travel time at 0 offset. The Taylor expansion of the TNMO is given here by the second equation. For small offset to depth ratios, TNMO can be reduced to a parabolic form, which is shown by the last equation here. This is a convenient form of an NMO equation for near offset reflections. We can note that it is a function of the offset, the velocity, and the reflector depth h, since h equals v p1 times t0 over 2. Also, if we know T0, the NMO depends on velocity only. This is another important result. The concept of NMO is used in various ways in seismic processing and in the interpretation of reflection data, as we will see in future lectures. Note that the formulae of NMO described for PP reflection are equally valid for SS reflections. We simply have to replace the P wave velocity by the S wave velocity. For the PS reflections, the travel time requires a new derivation due to the asymmetry between the downgoing P wave and the upgoing S wave, as illustrated here. Because of asymmetry of PS converted wave, the travel time in this case is not explicit in terms of offsets, as we have seen in the cases of PP and SS reflections. We are going to use parametric equations. In other words, we are going to write the travel times as a function of the ray parameter and offsets as a function of the ray parameters also. So the travel times and offsets are linked through the ray parameter. These type of implicit relationships are known as parametric equations. So by using the diagram on your left, we derive here the two parametric equations. Here are the final parametric equations. Thus, while the travel time for a PS converted wave in these equations are not explicit in terms of offset, we can still relate travel time and offset by the use of the ray parameter P. In other words, the travel time curve for converted wave can be determined by picking a value for the ray parameter and calculating both the travel time T and the offset X for this value of the ray parameter. The two values give 1 point on the travel time curve for this wave, since the ray parameter designates the angle of the P wave from the source, and the values of T and X obtained for this value of P are the values for that particular P. Note also that for a horizontal layer, the travel time curve for an SP wave is identical to the travel time curve for a PS wave. Again, note that given the locations of a source and receiver, the point where a PP reflection will occur is the midpoint between the source and the receiver for the single horizontal interface problem. As illustrated here, this PP reflection occurs at the midpoint, called CMP, because the downgoing ray and the upgoing ray are symmetrical in this case. For a PS reflection, this symmetry no longer exists, as we can see here. The midpoint is no longer the reflection point. In this case, the reflection point, known as the conversion point, or CCP, varies in a quite complicated way with the elastic properties of rock formations, in particular, the VP-VS ratio. Now, let's talk about refracted waves at the horizontal interface. Here are examples of refracted waves for PPP, PSP, PSS, SPS, and SSS. Notice that the refracted waves do not start at zero offset like reflected waves. We are going to derive a formula that is valid for all of these cases. Consider the general case. We have to describe the three parts of the ray path from the source to the receiver, that is, from A to C. We are going from A to B. V1 represents the velocity of either an incident P wave or S wave. That is, V1 equals P wave velocity of the top half space for an incident P wave. V1 equals S wave velocity of the top half space for an incident S wave. From B to C, V2 represents the velocity of either a refracted P wave or S wave in the high velocity half space. Note that V2 can also represent the velocity of the refracted P wave in the top half space if V1 represents the S wave velocity in the top half space. Finally, from C to D, V1 prime represents the velocity of either an incident P wave or S wave. That is, V1 prime equals P wave velocity of the top half space for an incident P wave. V1 prime equals S wave velocity of the top half space for an incident S wave. The travel time of a refracted wave is AB over V1 plus CD over V1 prime plus BC over V2. By using the definitions of critical angles, we can alternatively express the travel time offset relationships of refracted waves in the following explicit linear form. So we have a straight line just like for direct wave arrivals. However, this equation is only valid after critical angle. That is, when x is greater than x critical, which we will define next. Again, we have a straight line just like direct wave arrivals. However, this straight line starts only after the first receiver at which refracted energy can be received. This distance is referred to as the critical distance. The critical distance is obtained by converting the critical angle into the corresponding distance as described here on this slide. This figure shows an example in which direct wave arrivals are superimposed on refracted wave arrivals, confirming that refracted wave arrivals follow a straight line, just as direct wave arrivals do. The straight direct wave times and refracted wave times intersect at a point. At this point, the refracted wave overtakes the direct wave. The horizontal coordinate of this point, XCO, is referred to as the crossover distance. At XCO, the travel times of the direct wave and refracted wave are equal, and therefore we can deduce XCO. Now it's time for a quiz. Determine the travel time, the critical distance, x critical, and the crossover distance, XCO, of PPP refracted waves. Here's the answer using the diagram below. The particular case of P to P to P refraction corresponds to V1 equals V1 prime equals VP1 and V2 equals VP2. For this case, the travel time equation becomes T equals 2h cosine incident angle over the velocity of the top layer plus offset over velocity of the second layer. In this final form, the travel time equation is quite simple. It shows that the travel time equation of refracted arrivals is a straight line with a slope of 1 over VP2. Since VP2 is greater than VP1, the slope of 1 over VP2 must be less than the slope of 1 over VP1. The intercept time is obtained by setting x equal to 0 in the travel time equation. Now that we have the travel time, let's complete the crossover distance, that is, xco. At xco, the travel times of the direct wave and refracted wave are equal. We can then deduce the crossover distance. Let's conclude our quiz by computing the critical distance of PPP refraction. The calculation of the critical distance is straightforward. The critical time corresponding to the critical distance is obtained by dividing the critical distance by the direct wave velocity, Vp1. Now, let's continue the lecture. We have shown that the travel time of refracted waves for a single horizontal layer over a high velocity half space is a linear function of the source-receiver separation, that is, the offset. Here, we show that the travel time equations for refractions in deeper lying horizontal layers have the same form. Consider a sequence of horizontal layers in which the velocity increases with depth, as illustrated here. The equation for the refracted P wave in the ith layer follows from our derivations for the single interface. Let's add an important observation about reflection and refraction seismic surveys. Refraction surveys are based on refracted or head waves. Seismic refraction is applicable only where the seismic velocities of layers increase with depth. Therefore, where higher velocity, that is, clay, layers may overlie lower velocity, that is, sand or gravel layers, seismic refraction may yield incorrect results. In addition, seismic refraction requires geophone array lengths to be several times or approximately 5 times the depth of the top of the bedrock that we may be interested in locating. For all these reasons, seismic refraction is commonly limited to mapping reflectors that are less than a few hundred meters deep. By contrast, reflection surveys include all reflected and refracted waves, despite the inadequacy of terminology. Therefore, data resulting from the reflected surveys contain significant amounts of data, even for small geophone array lengths. Modern oil and gas exploration, with its large offset surveys, includes both reflected and refraction events. So far, we have focused on a single interface, that is, a 2/2 space problem. We now will expand our discussion to include a multi-layer problem for reflected waves. The one-dimensional medium can be approximated by many thin layers in which we assume the velocities and densities to be constant, as illustrated here. The Ray parameter P, introduced earlier, is given by sine theta over velocity, as you can see here. From this figure, we determine the horizontal travel distance x and the travel time t in terms of the Ray parameter, as you can see here. Thus, we have a relationship between the horizontal travel distance, x, and the travel time t for 1D media consisting of a stack of layers in terms of the Ray parameters p by means of the two parametric equations above. Let's now consider the case of a continuously varying velocity with depth. The expressions in the previous slide will give us the correct result by using the fundamental law of integral calculus if we assume the number of interfaces goes to infinity and that layer thicknesses tends to 0. Then we have the parametric equations in the continuous forms. Let's briefly talk about turning rays. In the above derivations, we assumed that there is a reflecting layer at depth z equals h to return the ray to the surface. Actually, it is also possible for a ray to return to the surface without hitting a reflecting interface, that is, turning rays. From this figure, we can see that at a certain depth, z0, the ray starts traveling horizontally and eventually turns back. The depth z0 at which the ray turns without the presence of interface is to the point at which the derivative of the depth with respect to the distance traveled is 0. In other words, the classical definition of a minimum for the ray curve gives us the turning point, and therefore z0. The turning rays play an important role in the illumination of complex geological structures, such as flanks of salt domes. Let's now discuss the important notion of RMS velocity. Let's start with this illustration. A and B describe a reflected event at z equals 1.5 kilometers for the case in which the background model above the reflector is heterogeneous. The travel time offset relation can be non-hyperbolic. C and D describe a reflected event at z equals 1.5 kilometers for the case in which the background model above the reflector is homogeneous. The travel time offset relation is exactly hyperbolic. E is a superposition of hyperbolic and non-hyperbolic moveouts after both travel time curves have been adjusted at the same 0 offset travel time. F is a superposition of straight and bending rays. There is a lot to unpack here. The basic idea here is that for 1D heterogeneous media, we can still approximate the two-way travel time variations of reflected waves with offset by a hyperbolic moveout, just like in the case of single interface. The trick is to find an equivalent homogeneous medium, which produces similar travel time variations with offsets as the 1D heterogeneous background medium. For 1D media consisting of N horizontal layers, we can introduce this new velocity, where delta Ti is the one-way vertical travel time through layer I. This formula allows us to predict similar travel time variations with offsets for 1D medium at a given interface. This equivalent velocity is known as the RMS velocity, or root mean square velocity. This is a very important result. Let me repeat it once again. For 1D media consisting of N horizontal layers, we can introduce this new velocity, where delta Ti is the one-way vertical travel time through layer I. This formula allows us to predict similar travel time variations with offsets for 1D medium at a given interface. This equivalent velocity is known as the RMS velocity, or root means square velocity. The interesting aspect of the RMS velocity is that it allows us to describe the time offset relation for 1D media by using the same hyperbolic form for the single interface problem. That is, travel time squared equals offset squared over RMS velocity squared plus the square of travel time at normal incidence, where T is the two-way travel time at the offset x, and t0 is the two-way travel time at a zero offset. Note that the time offset relation is valid only under the small offset approximation. Let's now look at some examples to provide more insight on the usefulness and limitations of the hyperbolic approximation based on RMS velocity. Here we show one 1D heterogeneous model and the equivalent RMS velocities obtained by using the formula of RMS velocity. We can notice that the RMS velocity model increases with increasing time or depth, even when the actual velocity is decreasing with depth. Actually, this conclusion is valid for most 1D realistic geological isotropic heterogeneous models. The RMS velocity model always increases with increasing time and depth. Here we show another 1D heterogeneous model and the equivalent RMS velocities obtained by using the formula of RMS velocity. We have the same conclusion. We can notice that the RMS velocity model increases with increasing time or depth, even when the actual velocity is decreasing with depth. Actually, this conclusion is valid for most 1D realistic geological isotropic heterogeneous models. The RMS velocity model always increases with increasing time and depth. Here is an illustration of an exception to this rule. We can see that the example in this figure are geologically unrealistic, except in some deep waters with an unconsolidated sea bottom. For example, the model in this figure assumes that the velocity decreases just below the seafloor to a velocity smaller than the velocity of water. The RMS velocity will increase with time or depth as long as the velocity at the layer in is greater than the RMS velocity associated with the layer above the layer in. Let's now look at how the RMS velocity can be used to predict the travel time variations with offsets for the 1D heterogeneous models shown in this figure. The results here show a good match between the travel time variations with offsets predicted by the 1D heterogeneous background model and the ones predicted by a constant RMS velocity, especially at small offsets. However, we must reiterate 2 points. The first point is the RMS velocity model is used to predict the travel time variations with offsets only. In other words, the amplitude variations with offsets are not properly predicted when a 1D heterogeneous velocity model is replaced by the homogeneous RMS velocity model. We can also notice that the travel time at the zero offset is often not properly predicted by using the RMS velocity, as we can see here. So in practice, we will use the RMS velocity for correcting the Moveout, that is, travel time variations with offsets, without modifying the amplitude variations with offsets and without changing the travel times at the zero offset. The second point is related to the fact that the hyperbolic Moveout formula is valid only for the region of small offsets, where the behavior of travel times with offsets is hyperbolic. In fact, we showed earlier that the equation of travel time variations with offsets for a single interface problem is a hyperbola. So when using the RMS velocity model, we are treating the heterogeneous model as a single interface problem. Therefore, the travel times predicted by using the RMS velocity behave hyperbolically with respect to offsets. Unfortunately, this is not exactly the case for heterogeneous media. The travel time variations with offsets in 1D heterogeneous media behave hyperbolically only as a second-order approximation. In general, these travel time variations with offsets are non-hyperbolic for heterogeneous background velocity models. The travel time differences are clearly noticeable at large offsets in this figure between the travel times predicted with a 1D heterogeneous background velocity, and those predicted with a constant RMS velocity are the differences between the hyperbolic and non-hyperbolic moveouts. The sub-basalt model of the subsurface is one example in which the non-hyperbolic behavior of travel times with offsets is quite severe. This figure shows a simplified model of the sub-basalt and the equivalent RMS velocity model. Based on these velocity models, we simulated the travel time variations with offsets. We can see a significant deviation from the non-hyperbolic curve related to the 1D model with respect to the hyperbolic curve related to RMS velocity. Notice that these deviations from the hyperbolic travel time behavior generally increase with increasing velocity, heterogeneity, and they are closely linked to the degree of ray bending. The presence of a high-velocity basalt layer in this model is the reason for the deviations from the hyperbolic travel times. In summary, the hyperbolic moveout describes a linear relationship between square travel time and square offset. This relationship, assuming that the ray from the source to the reflector and the ray from the reflectors to the receivers are all straight rays. The non-hyperbolic moveout describes a nonlinear relationship between square travel time and square offset. This relationship, assuming that the ray from the source to the reflector and/or the ray from the reflectors to the receivers are bending rays. So here is the expression of RMS velocity associated with straight rays. The second equation recalls the hyperbolic moveout. We can also notice that at zero offset, the travel times are not necessarily valid under homogeneous medium assumptions. Therefore, the RMS velocity may not allow us to predict T0 if we know H and V RMS, but we generally know the correct travel time at x equals 0 from seismic data. For completeness, here are the RMS velocities for converted waves. We have introduced the notion of RMS velocity for 1D heterogeneous media. Our next objective now is to describe the relationship between the RMS and interval velocities, that is, Dix formula. Here is the formula which allows us to derive the actual velocities of the medium, also known as interval velocities, from the RMS velocities. This equation is known as Dix formula. We remark that using RMS velocities as if they were average velocities can lead to significant errors in depth estimates. For completeness, here is Dix formula for converted waves. The subsurface does not consist only of horizontal interfaces between rock formations. The interfaces can vary laterally, that is, a dipping interface, for example, and even discontinuously. Here we illustrate the effects of a dipping interface on travel time arrivals of reflected waves. The derivation of the travel time equation for a single dipping interface is essentially the same as for a single horizontal interface, but with one key difference. In a single horizontal interface, if the vertical and horizontal distances between the source and receivers are known, we can predict the travel time arrival. In the case of a dipping interface, we will also need the source position relative to the receiver position, in addition to the horizontal distance between the source and receivers, or the offset. The terminology commonly used for this problem is the downdip position, when the receivers are located on the negative x-axis with respect to the source position, shooting updip, and updip when the receivers are along the positive x-axis with respect to the source position, shooting downdip. Let's first tackle a scenario in which the source position is located in the downdip position, shooting updip, and deduce the updip position. Using the ray diagram, we can obtain the travel time of this case in blue. Notice that when the dipping angle is 0, we are back to our horizontally flat case. Our next step is to move the source to the updip part of the interface to shoot downdip. As one might expect, the equation we arrive at looks similar to that of updip shooting. Refracted arrivals can be used to predict the thickness of weathered layers in land seismics using the intercepts of refracted waves. Unfortunately, the travel time curve of a dipping interface is a straight line, just like that of a horizontal interface. The solution to this problem lies in updip and downdip shooting, but more particularly in the use of intercept times instead of slopes or gradients, as the travel time offset relationships are linear in these cases. Let's now look at the travel time equations of reflected waves over a dipping interface. This figure illustrates a reflection on a dipping interface. To maintain the conventions used for the derivation of refraction equations, the dip angle is taken to be positive when the slope is upward and toward the right. Please pay careful attention to the diagram in order to capture what I'm describing. A useful trick for the derivation of reflected travel time equations is the concept of image point. If we imagine extending the line AE, which is perpendicular to the dipping interface, an equal distance on the opposite side of the interface, we would be given the line EQ, which is also of length Z. The image point is at Q. If we now draw a line from Q to C, which is the geophone position, we have a particularly useful geometric construct. Because triangles AEB and DQB are congruent, AB is equal to QB. Therefore, the path QBC is equal in length to the actual path traversed by the reflected wave ABC. Let's analyze the effect of dip. This figure shows the travel time curves for alpha equals 0 degrees and alpha equals 20 degrees. The travel time curve for the horizontal interface is symmetrical with respect to x equals 0. We can see that the minimum time on this hyperbola is no longer at x equals 0 for the dipping case. There is an interesting concept in seismic data processing related to using the displacement of the hyperbolic form of a travel time curve when dealing with a dipping interface. This concept is called dip moveout, or DMO. It is the difference in travel time to receivers at equal distances from the source position in a split spread geometry. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode Education lecture.